Good afternoon, everyone. And let me start by thanking Professor Tarun Souradeep. Despite from being having a very busy schedule, he's able to give this talk, though online. But we all know that he is very busy person these days, especially heading the institute, the premier institute like Raman Research Institute. And I'm also thankful to all the participants, enthusiastic participants, who want to know about cosmology and especially the CMB. So there's a lot to be told about Professor Souradeep. Even his brief CV is, I think, about 20 pages, and my longest my longest CV has only 5 pages. So you can see. So briefly telling, so if I tell you that the guy who is going to tell us about the cosmos was for a short duration working dealing with the engines at Aisher company in Delhi. So he started as an engineer, but he is among those rare person who left engineering to pursue the physics and mainly the astrophysics. So he obtained his B.Tech in mechanical engineering from IIT Kanpur in 1988. Then he moved to Pune, to Ayuka basically, to finish his master's and PhD. And he has been, if I am right, the first student of Professor Narlikar.
No, one of
Okay.
the last students.
I see. But
And
first student at
it,
IU.
I was
Yeah,
the first graduate student at IUCAM.
yeah, the first student at
Yes.
IUCA. Yeah, so he did his finished his PhD long back in 1995. Then served as the postdoc at CETA in Canada and Kansas University. He joined IUCA as scientist D in 2003 and worked there for a very long duration till 2019. In 2019, he left Ayuka to join as a chair of Department of Physics at IISER Pune. He worked there until Jan 2022, and for past 2 years he has been serving as the director of Raman Research Institute. So he has done everything what a great academician should do. He has published a lot of paper. He has trained PhD students, postdocs, has taught several courses. But apart from that, he has not just groomed the student, but he has also groomed, I will say, many big science projects. To name a few are the LIGO India. He has been the spokesperson for LIGO India or Indigo Consortium for a long time, and he has also been instrumental in bringing up the project which is called as the CMB Bharat. So without too much ado, let me give it to Professor Souradeep for the talk. Over to you.
Thank you, Gurudat. Thank you for the invitation. I always am delighted to speak to young people because, as Gurudat says, one of the passions I have is to train students. I've had a lot of students, and also the kind of projects that we are pursuing are largely for the next generation. Okay, so this is to make sure India is part of the absolute frontier science work, and we are taking on projects which are ambitious and also long future. My interest is in cosmology. That's what excites me about the universe. And so, you might ask why, and I don't have too many answers to it except to show you this beautiful picture taken the from Hanley in Leh, Ladakh, by the person who runs the observatory there, the Jeanchu, a high altitude observatory in Hanley. And you can see that it's a spectacular world outside. While we worry about many, many minor things in our little planet, we should always remind ourselves that we are really riding on a tiny speck of dust in the middle of a vast and very, very interesting universe. So I'd like to take you on a tour of that, how vast is the universe, and when you look out. So I titled my talk mainly on the phrase that was used for the Nobel Prize in physics in 2019, our place in the universe. And there are two parts to that. One was about the discovery of new planets, Earth-like planets, and this is exoplanets, which kind of suggests that there could be life elsewhere in the universe. And the second part was that this was the first two gentlemen here, Kilos and Mayer. And the second one was the third person on this was James Peebles. James Peebles, as he's well known. So my talk, I will not dwell on the first work of the first two to keep it simple and talk about why we gave a Nobel Prize to understand, to appreciate that scientists now understand the universe so well and from just the vantage point, as I said, of a real speck in the universe, speck of dust. And this is what Jim Peebles had to say in 1988. The universe is simple, it's expanding in a computable way, which is an amazing thing. I would have never anticipated it could have been worked out so easily, but there it is. And this is an amazingly humble statement because it is true that who would have thought that human beings sitting on planet Earth would have the means to probe the universe and have a cogent physical model which seems to explain everything that we are seeing in the universe till now. We don't have anything that seems to require anything beyond the model that we have put up. Again, so let me talk about the cosmic stage. So this is another grand picture of the Milky Way, now reflected in a lake. And just to tell you why I believe that the study of cosmology is as old as humanity, because I'm sure even the cavemen, in fact, they were luckier because they could actually see the Milky Way. Most of us sitting in cities in India and elsewhere also do not have the benefit of seeing such spectacular skies, clear skies, night skies. And so here it is, a vast universe waiting to be discovered. So what we learned, and not too long ago, just about a century and 10, 20 years, 120 years back, is that the universe is much more than the island of stars that we see around us, which we call the Milky Way, Akashganga, right? So this is what we are seeing. But all this, most of this light is from our own galaxy, right? And then we need to ask, is there anything beyond? And so you look away from the galactic plane, where most of the stars are, to a dark spot in the sky, okay, where you don't see any stars or anything, okay, and very little tiny patch, and you look at it and look at it through the most powerful telescope we have. So I keep upgrading this picture. This is the James Webb's deep field image. And you can see that little patch of the sky. If you probe it deeply enough, more with sensitive instrument, you see the universe is full of galaxies more like ours. Okay, here some of them come in very funny shapes. That's because that's Einstein's gravitational lensing at play. There are galaxies which are fairly. Can you see my pointer by any chance?
Yes, sir.
Okay, so you can see that these galaxies are more or less like what we think galaxies are. But if you really look at the red dots there, they are very tiny. I mean, there are tens of thousands of galaxies in this picture. You can't pick all of them by eye because but you can see some splodges here. These are all galaxies, distant galaxies, and they are really irregularly shaped. And that's not because galaxies were different then. It's just that light takes a long time to come from there. So we are seeing them as they were just forming. Okay, so we are looking almost to the edge of when the first galaxies formed in the universe. Okay, and the universe from there to here is full of galaxies. And so it's obviously a very humbling thing that we are one of such galaxies among billions of galaxies that we know exists in the universe. If small patch of sky reveals tens of thousands, you can imagine what it must be like. Now, before I move on to the distribution of galaxies, let me tell you, a galaxy is quite a non-trivial thing. It's not a simple object. You know, this is the picture of a neighboring big galaxy, Andromeda, and you can see that there's 100 billion stars there in that galaxy. It's a bound structure of gas and stars moving around. Light takes about anywhere from 30 to 300,000 years to go across the galaxy. And light travels at a very high speed, right? So from our sun, it takes 8 minutes for light to reach us. But we are now talking about distances in light years, because that's kind of the, otherwise you will have two big numbers in the thing. And each of the stars that I talked about in the galaxy are themselves massive structures. See, our entire humanity and culture and everything, and the very fact that life exists on Earth, depends on one tiny ordinary star, which is the sun. We even worship it. Most cultures have learned to worship it. Imagine that this galaxy has 100 billion such stars, and many of them have planets around it. And maybe there are many of them which have some, intelligent life, which is also doing something similar, or maybe more intelligent than us and not worry about, believing in, religion being very important. But whatever, they are doing what they want to do. And there's a lot of interesting things that are bound to be found as we look out. So here, what I have done is a map. So normally when you go to a city, you look around and see where are most of the, restaurants or something like that. Similarly, if we are looking around out from our solar system, okay, this is the local area within our galaxy itself. And you can see that there is a lot of structure around us. We are actually in a bubble, and then there are very, very interesting structures in which mass is distributed. Mass is not uniformly distributed around us. But I just wanted to point out the light, the scale here. This is 650 parsecs. So if you multiply by it at 3.26, it's about 2000 light years. So we are already talking about distances that in normal human experience are just out of bound, right? I mean, we never we our entire after AD period has been 2000 years, right? So light from that edge coming to us, came when Jesus was crucified. Okay, so this is the solar neighborhood, and we have absolutely fantastic data which allows you to make, and this is from a satellite called Gaia. Okay, now let's go beyond our galaxy. Okay, now our galaxy is at the center. You don't worry about anything else. All these dots that you see are major structures where there are multiple galaxies. The Virgo cluster of galaxies, Perseus, Pisces supercluster, Vela. So you can see around us, matter is clumped. And if you go further, zoom out. Now, if you have been watching, I've been putting a stick here, which is 100 million light years. So we're talking about 100 million years for light to come from the edge of this picture to the center, right? Now, in few hundred million years. Now, the 100 million years has become this small, right? And then now you see this cloudy structure. Each dot here is a galaxy, and this is the Hercules supercluster, Shapley cluster. So you can see that what we have in the middle of is a vastly interesting distribution of stars which are sitting in galaxies, and we see them because stars give out light. And these galaxies are not smoothly distributed, they are distributed in a very interesting pattern, right? You can see this bubbly pattern. And now, if you really want to take a fly through, the universe, some magic way you can do that, or some Star Trek way, this is what you would actually see. You can see that there are galaxies which are, forming clusters, and then the clusters are linked by filaments of galaxies, and it's what is called the cosmic web. Okay. And you can, imagine the grandeur of, the universe that you're trying to look at, right? And remember, each galaxy that is whizzing past has 100 billion stars, and we are sitting around a ordinary star in an ordinary galaxy amongst all of them. So let me move forward and tell you, this is kind of called the Atlas of the Universe. So this is kind of a map of distribution of matter in the universe that we have mapped out. We can see this distribution in galaxies. And what is interesting about it is, let's look at a typical place. There's this box. I have said, let's choose a box, and I could have placed it anywhere. Typically, such a box would look like this. It would be full of galaxies, but these galaxies will be organized in some kind of very intricate structures, right? And these are typically, in studies of phase transitions and all, you see such interesting structure. But this is not phase transition here, but nevertheless, galaxies. And this is real data. This is from the 2 degree field uh, uh, survey many years back, about 20 years back. Now, you might want to ask, how do I ever understand such a complicated universe? Right? And this is where I think the strength of physics comes in, the strength of human ingenuity, which of course has physics and mathematics. And I want to tell you what's so special about physics is, when you're faced with a complicated problem, you try to abstract out the main elements out of it. Look for the simplicity in it. So many of you who are undergraduates would remember that when you solve various equations of, ball rolling down an inclined plane, you often use approximations like friction, zero friction, uh, things like that. And these are the simplifying assumptions you want to, but that captures most of the physics that you want to do. Similarly, now if you wanted to understand the universe, you'll have to see, is there any simplicity that I can bank on? Because otherwise, it's a vast universe, very complicated structure of galaxy, distribution of galaxies. The simplicity was very quickly recognized, and initially, of course, proposed as a theoretical simplification for the model. But the beauty is, if I project all that, I don't worry how far the galaxies are, but where they are on the sky. Then even in the 70s, we had fairly good sky maps. This is a picture from Peebles' books, which I like very much. So you can see it's the two hemispheres of the sky. There's a part which is cut out, and that's because we, at that time, we couldn't look through the plane of the galaxy and see these stars, distant galaxies. Okay, and now you can see these galaxies. Although you can see some kind of a structuring there, on the whole, there is no direction which is crying out for attention, right? It's not as if the universe has a particular direction in which there are more galaxies, and in some directions there are extremely low number of galaxies. More or less, if I averaged it, and as I keep saying in most of my talks, if you take off your glasses, if you have glasses, you take them off, and you'll see more or less a smooth white patch on both the sides. Okay, so what can you make of that? Okay, what we can assume is, in any direction that I'm looking in the universe, the average number of galaxies in that solid angle is the same. So there are as many galaxies in one direction versus another. There's no preferred direction in the universe around us, because we can't go to any other very distant place and see the universe. Now there's a leap of faith. So, and this is, I would say, a super Copernican idea. So Copernicus told us that don't think the universe revolves around the Earth. Don't be so, kind of anthropocentric, that everything revolves around the Earth. Actually, in the solar system, everything revolves around the sun. So similarly, we can say that Earth is not special. So we'll say our galaxy is not special. So if we see a isotropic distribution around us, and for an observer sitting on a distant galaxy far away, he or she would also see a isotropic distribution. And then you use a mathematical theorem which says a medium which is isotropic around every point is a homogeneous medium. Okay. While it sounds fairly straightforward, these are fairly deep, implications, and we are still checking how good these approximations are. But this is what we started off in building cosmological models by invoking something called the cosmological principle. At that time, in 1920s, we didn't have such spectacular maps of the galaxies in the universe. And they led to the basic underlying models of cosmology called the Friedman, Lemaitre, Robertson Walker models. Okay. And where did they come from? They themselves were an absolutely amazing discovery for human beings. Okay. You know that Einstein's general relativity said that gravitation is nothing but the curvature of space-time, and that curvature of space-time is created by matter. Now, the simplest problem that you can solve in general relativity is cosmology. So you assume that there's a uniform distribution of matter and ask what will the space-time of such a, in such a case would be. Okay. And that led to a absolutely surprising result that it was very difficult to get a universe which is static. The universe would either be expanding or contracting. Okay. And so a uniform distribution of matter on cosmological scales lead to a smooth expanding universe. And this was so radical at that time that Einstein himself abandoned it and tried to create a model which was static by invoking something called the cosmological constant, which incidentally is also important now, as I'll tell you later. But this is the picture you should have. So I like to show this picture every time because most of you who have tried to find out about cosmology may have seen BBC things where they show the early universe like some roar and explosion happening. But it's not that there's an explosion happening. What we see is, yes, galaxies are moving away from each other, but the picture, more correct picture, is the space itself is like a fabric which can expand in time. This is what general relativity allows, our understanding of gravitation allows. And it's smoothly expanding, magically expanding due to the presence of matter. And you can see that there are these green dots which are moving away. But if you were to move the green dot to another place here, around that also, that every galaxy will, when it looks out to its neighboring galaxies, it will see them receding away from each other. Okay. So I'm not sure how many of you are familiar with space-time diagrams, but this is a way to plot this distribution of galaxies, okay, which are expanding away. So what we have done is, in space we have factored out the expansion factor, and in time we have also factored out the expansion factor. In that case, you see that you have something like this: the time ticks faster as the universe expands, but otherwise most of it is consistent with special relativity. In case you have done it, that's fine, but I won't really dwell on it much. But this is what is called a space-time diagram. It tells you, like, from here, when I'm looking back all these galaxies, I'm can look back only along these red lines. This is the line along which light goes. So whenever I look at a distant galaxy, I'm seeing it as it is in the past. And also, interestingly, light from it is redshifted relative to the light here. So if there is a hydrogen line emitted from here, that hydrogen line will appear much longer wavelengths when it is compared to hydrogen line uh, in an apparatus on Earth. Okay, so we have space which is expanding in time, so we can draw a curve of how the space expanded in time. And time, of course, as you realize that if distances are in billions of light years, then the universe is talked about in billions of light years. So this is how the space expands in time in this model. And you can have various scenarios. The space can expand up to a particular point and then start contracting. It could expand and then keep expanding at a constant rate, and at a rate which will slowly go to zero. Another one, the blue line, is it will keep expanding at a constant rate, and this red line is it expands and then and it's expanding with a deceleration, in the sense the expansion rate is going down, and then it turns around and the expansion rate, the expansion of the universe accelerates. And this is the red line. And what we knew even from the basic theory was, if I were to look at all the density of matter in terms of their critical density, and we usually use this capital omega to say that. And critical density is some characteristic density of the universe, which is given by the expansion rate of the universe. Okay. And we ask at this time, what is the expansion rate? So we will have the critical density. And then ask, in terms of that critical density, how much of the matter distribution in the universe gravitationally clusters and how much it doesn't. How much doesn't, right? So this is matter density. This is often called the vacuum density or the cosmological constant. And so we have a simple model. Now the question is, how do we choose which universe we are on, right? Remember, we are sitting on a speck of dust spatially, and in time also, we are, not spend more than 100 years worrying about cosmology. Okay. And so what really happens in an expanding universe is that physics as we know it is applicable, but you have to remember the space expands. So it's as if we are doing physics on an expanding fabric. So let's look at this consequences of that. So suppose I mark out some galaxies in a particular volume now. Okay, as I go back in time, that volume was smaller by say half. Then the number density of galaxies would have been higher by 8. And if you do mc square, mass into c square as the energy density, it will be also 8 times what it is now. And if you go to a time when it was 1/4, it will become 64 times the number density and energy density. Okay, this is for the galaxies and the rest mass of the galaxy, rest mass energy of the galaxy. But look at light. Light behaves in a slightly different fashion. If you look at this box of light, when the universe is half its size, the number of photons here would go up by a factor of 8. But all the photons, their wavelengths have become half of what it was before. So then the energy density actually goes up by an extra factor of this relative length scale. So it becomes 16, 128. So you can see that even if we start with the universe as we see it now, where the rest mass energy of the galaxies exceeds the radiation density in the universe by a factor of 10 to the power 4. Yet, if you were to go to a universe which was 10,000 times smaller in size, at that time the rest mass energy in matter was equal to that in radiation. And for any time before that, the universe was just dominated by that radiation density. The early universe is very simple. You don't have to worry about galaxies or anything. You just have to worry about how much radiation density does the universe have. Okay, these are all things we had worked out. But the question is, where is that radiation? Okay, and this was very serendipitously discovered when they were building the first radio telescopes. And Bell Lab built a telescope where they could get rid of a source of noise, which seemed to be there at all times, whichever direction you pointed the telescope. So it was an isotropic distribution. And also, we believe, if you believe the cosmological model, it's a black body. It's a special kind of a distribution, which is only characterized by temperature. And from that, you can read off the temperature of the universe. And the temperature of the universe in the radiation, dominant radiation content, is about 3 Kelvin, right? Very cold now. But remember, 3 Kelvin temperature, when I go to universe 10 times smaller, will become 30 Kelvin and will keep climbing as we go back to the past. Okay, so this was the first Nobel Prize that it won. So now we had a great thing. So we knew matter density, the radiation density, we could count up the galaxy. And then you can start trying to see, predict what will happen in the universe in the past. And also you can predict what will happen in the future, but you can also try to reveal what kind of physics, because physics is the same. Up to this point here, till the universe was about 10 to minus 30 seconds old, most of the physics is fairly well understood. Okay. So we have a picture, a model of the universe where we understand what it is like now and what it has been in the past and what all can we look for. So things like James Webb Telescope is looking at structures that are just forming somewhere here, just at the end of dark ages, what is marked as dark ages. Okay, and then there are other experiments, and particularly in RRI, which are looking at it a little beyond that. So we are probing it from this side with James Webb, from this side with neutral hydrogen. Okay, so we are in a situation where we are sitting here at a distant time, but using this time machine, because light takes time to come to us, we can probe the history of the universe and its evolution. So where is this radiation coming from? Again, there's a space-time diagram. Again, I don't know how many of you are familiar with it, but this is the same, uh, lines that I showed you in red in that space-time diagram earlier. Now we are here and now. As I go out and look into the distance universe like this, I'm looking at the past because I'm looking along what is called my light code, backward light code. And slowly I will come to a point where the universe was 1,000 times smaller, 1,100 times smaller. Okay, now we know how much of hydrogen and helium is there and what is its density now. If you project that and look at what happened and the temperature is 3 Kelvin, here is 3,300 Kelvin. At 3,300 Kelvin, basic physics tells you that um, hydrogen and helium will be totally ionized. So as you know, it will be a plasma, and your instructor here, Gurudat, professor, he is an expert in plasma physics from the most well-known institute in India. And so he will tell you why plasma is totally opaque. So when you can look up to this thing, plasma, when it forms a plasma, you can't look beyond because light, it is made of charged particles, and light scatters around just too much. So just like in the fog, you can't see the headlights beyond. So no cogent information can be found from this period before this. And this light that is coming from this red circle here, now that red circle, this is a 2 plus 1 dimensional, two spatial dimensions, one time. But this is, of course, we know that we are in three spatial dimensions and one time. So this circle will become a sphere around us. And we will have this picture. So we are here now in a universe which is 14 billion years old. Okay, giga is a word for billion. We can peer out 43 billion light years to the surface where we see a glowing plasma. The plasma, if I were to take a thermometer and measure it, is glowing at 3,300 Kelvin. But the expansion of the universe makes that same radiation, much, much colder at 3 Kelvin here. But this is the region of the universe that you can probe electromagnetically. Beyond that, the plasma wall completely shields the early universe from it. But this is also good because this is super IMAX theater from where the cosmic microwave background is coming. So till from 65 when it was first discovered till 92, we only saw a uniform glow. And I don't think any of you would like to sit in an IMAX theater and just watch a glowing screen. You want some action on it. And that happened in 1992. And that was almost a year after I started my PhD, year or two after I started. Okay. And this is the Cosmic Background Explorer, which told you that not only is this exactly a black body to a amazing accuracy, but it also had fluctuations. The temperature in different regions of on this plasma screen had a little different temperature at the level of 10 parts per million. And that was necessary because we know that the universe now is not homogeneous. I told you there are rich structure in the distribution of galaxies. And if there has to be structure in the distribution of galaxies, there must be some imprint of that in the radiation of the universe. And that is the imprint that we discovered in 1992. And these are called cosmic microwave background anisotropy. Okay, because there's small differences in the temperature of the microwave background in different directions. And this connects the universe at 500,000 years old, when it was only 500,000 years old, to the universe now, which is 14 billion years old. Okay, and explains how these galaxies form this rich, intricate structure. Okay, and this is the story I'm going to tell you. So this is the story of how cosmic microwave background unraveled what the universe is for us. Okay. The other thing that is still to be unraveled, and is the next part, I mean, that of the story. So it's not that we have ended the story. It is, just the first one. Like, you have these sequel movies, right? Bahubali 1, Bahubali 2. So, we know this part of the universe and the connection from this surface with this. But we know something created these perturbations in the first place. There's some mechanism, some early universe physics, which we still have to discover. Okay. So some numbers. So this thing, which is glowing at 3,300 Kelvin is actually now 3 Kelvin bath that we see. The fluctuations in that 3 Kelvin are at the level of 70 microkelvins. So as I said, one part in 10 to the 5. And then there are interesting polarization information, which I am not going to talk about much. Okay, so since the first discovery, as I told you, this also coincides with my own career. From 91 to 94, the Cosmic Background Explorer mapped out these anisotropies, but with a very low angular resolution. It was like you're looking at these fluctuations, or you're looking at the IMAX theater, but you had forgotten your glasses. Then WMAP gave you glasses which were halfway as good. So you started making out pictures in this distribution of temperature in the universe, on that IMAX, on that plasma screen. And then we had another space satellite called PLAN, where we were also part of the whole collaboration from India, which has now the most refined picture of this plasma screen with very high resolution, image of the fluctuations that are there in the microwave background. I should also mention, while these were the milestone space missions, there were many, many, many experiments which did fantastic observations from the ground. And these are stories in themselves. But the story has not stopped. So you can see that there's a relentless march. So, this is Planck when it was taking data. And now we have things where, experiments running on the South Pole at this time, which are orders of magnitude much more sensitive than Planck, right? And revealing more and more about this cosmic microwave background. So, what did we learn from this, measurements over the 3 decades? What I would say, without getting into the details that are given here, is that we now have a very good idea of a model of cosmology that works. I know I told you a lot of curves were possible. We know which of the curves actually the true curve, and also we have established a lot of the assumptions that we have put in the cosmological model. Okay, so this is a beautiful picture from the Planck collaboration, which shows you the temperature fluctuations, but more importantly, the intricate weave of polarization information. But I'm not going to talk about that at all today. Okay, but what you can do with these is this is a random fluctuation in the sky, and whenever you have some random distribution, like suppose you're given a table and someone says how smooth it is, you measure the deviations and then give me an RMS. You say root mean square of fluctuation is at uh, say a micron. But then a table which is kept out in the rain will have that micron level things at small scales. But on large scales, the table will get warped and there will be deviations which are at larger scales. So similarly, you can ask at different angular scales, how much is the fluctuation in the temperature and polarization information? And these are called angular power spectra. So for any model of cosmology that I had, I can draw a curve like this gray curve, right? So let me take a universe with a particular amount of cold dark matter, ordinary matter, expansion rate, and various parameters like that. And then I can draw this gray curve. But what we have measured from Planck are these green curves, right? And the game we played for quite some years is to keep dialing these values of the parameters, like how much of cold matter, what combination of the parameters gives you the best fit to all the data simultaneously. This is the Planck angular power spectrum in green. Okay, and you see that you can do that with computers, with Markov chains, very interesting field in itself of computer science. And you can see that I can vary them in a very interesting pattern and randomly search and home in on a model which is the best fit to all the data. So this combination of cold dark matter, barrier, ordinary matter, expansion rate, and all that explains the universe. So I just need 6 numbers to explain what I see on that plasma screen. Okay. And we have a lot of faith in this because, as I told you, the physics we are using is very basic physics. It's very well understood. So let me give you a flavor of how simple the physics is. Okay, so this is the music of the cosmic drums. I told you the universe is like a fabric which is expanding in time. So you can think of it like a membrane of the tabla. Now you would wonder what do when a musician is there, you know, you cannot make out whether the tabla is tuned or not. But how does the musician get to know of it? You'd see them tapping it with a hammer, right? So that is called a green function. So you try to look at the response of the system. So you're looking at the plasma and how it responds to perturbations. So this is how the plasma responds to perturbations in the early universe. You can see that the ordinary matter and radiation actually go out and start traveling in a ripple till about a time when the universe became transparent. When this is red, the universe is in the plasma state, and then the plasma turned neutral, and then this ring doesn't go any further. So the analogy I can give you to this is imagine that you are in a lake which is completely placid. There's no movement of water, and suddenly there's a burst of shower. Right around every point that a raindrop falls, a ripple will go out. And suppose you were to take a picture of this water 10 seconds later, you will actually see completely choppy waters, which is equivalent to what we are seeing. We are seeing a random distribution of fluctuations of temperature in the sky. But as physicists, we know that those fluctuations are made up of this spike in the center and a ripple. So if you have that information, you can actually deduce what really was the characteristic of this plasma surface then. Okay, and we know that these rings that are there in this plasma screen image have a characteristic scale of 150 megaparsec. And you can use that to probe very interesting things. You can ask if the universe is uniform, but is it uniform positive curvature or uniform negative curvature? And we know if it is Euclidean in the sense that angles of a triangle add up to 180 degrees, then the temperature, RMS temperature would be 74 microkelvin at the peak. Okay, and this is also the baryon density will be 74 obviously. And if it was flat, then this peak will be at an angular scale corresponding to an inverse angular scale of 220. So we have been making these measurements, and these are early results from 2006, where we also reanalyzed these results from WMAP, and you could clearly see that the location of the first peak, which tells you the amount of ordinary matter in the universe and the geometry of the universe, is fairly well mapped out even then. Okay, and you can deduce from there that the universe was flat geometry, Euclidean geometry, where angles of a triangle add up to 180 degrees. And the amount of ordinary matter in the universe is only 4%. Rest of it is matter that we don't even know about it yet. Okay. So this is the thing. So there are three possible geometries of the universe. The universe could be a uniformly expanding sphere or a uniformly expanding hyperbolic surface or a flat. And we know for sure it is this flat surface. Okay. Which kind of tells you that now I have to only worry about how much of matter which clusters and does not cluster. And that we have already had a fair idea because we could take distribution of matter, run simulations, and ask in different universes how would the simulations grow. And if you really look at it, we already knew that the universe distribution of galaxies in the universe look more like this picture in the upper one panels than the lower panels, which tells you that the amount of clustering matter in the universe is only 30%, 0.3. Okay, and the total energy density of the universe is unity in that unit, and it's the critical density. So now we know of the two guys, we know that the three guys, we know the curvature density is 0, we know the matter density is zero point 0.3. Then we are forced to accept that the uh, there is energy density in the universe which does not cluster under gravitation, which was not something that we expected. But we are forced to this conclusion that 70%, the dominant component of the universe, energy density of the universe, actually does not cluster under gravitation. So you see that we know a lot now from this Planck. I showed you those green maps, but this is the actual, measurements of Planck as presented by them, the collaboration. You can see these very intricate, exquisite measurements where you not only know the first peak, but second peak, third peak. So you can figure out all the parameters of the universe to amazing accuracy. So we know the amount of ordinary matter to a percent accuracy. We know the amount of cold matter, cold dark matter, which is basically the matter that clusters under gravitation, but is not baryonic, not ordinary matter, is 2%. We know the expansion rate to 1.3% accuracy. So this is unprecedented situation in cosmology because in 1990, when I started working in cosmology, this number in particular was known to a factor of 2. There were great uncertainties in this number up to a factor of about 10%. Okay, so now finally, what the microwave background sky and its fluctuations have given us is something we can call a standard cosmological model, a model that fits all the data. Okay. And it is based on very simple assumptions, as I first told you. But yet, you see, a simple model need not be something that reveals simple things. I told you, Einstein's general relativity is a beautiful, simple theory. Simple in the sense that, idea is very simple, but it revealed that the universe is expanding, space-time curves. Similarly, when we applied it to the universe, we had a simple model, but we have an exotic universe. 95% of the universe is in some exotic form, which we don't know about yet. So there's a lot more research to be done. So we have dark matter that we cannot see it, but we do see its gravitational effect. But dark energy is even more mysterious. It's a smooth form of energy which acts repulsively. It doesn't cluster under gravity. Okay. So although we have learned a lot about cosmology, we have also opened up questions which are big. So there are active searches for dark matter, and there is this satellite which has gone out called Euclid, whose primary goal is to understand dark energy, try to reveal what the dark energy is. But I will focus on the third thing that is revealed. See, all this thing, if you remember the picture where I showed you uh, you know, the sky, that is CMB sky, and then I showed you something creating fluctuations in the early universe. We know that some ultra high energy physics is still missing, which creates these primordial perturbations. Okay, so this is the question we are also posing. One of the questions. One is to ask, what is dark matter, what is dark energy, but also who pinged the drum. So as I told you, the Tabalchi actually hits the drum with a hammer to make a vibration, and so in some sense, the space-time fabric was perturbed in the early universe by some process which we don't understand, but we see its effect on this cosmic screen, which is the microwave background or the IMAX theater that I was talking about. And from there, we know how to evolve to galaxies now. This is 380,000 years in the history of the universe, and this is 4 billion years. So you can, it's like looking at a 1 day old baby relative to this old guy here, 100-year-old guy here. And then we have also started having bold ideas for the last few decades on what really generated them. And that is quite something very, very amazing, right? It's a fantastic idea that every structure that we see in the universe originated from quantum fluctuations in the early universe. Okay, and then this era where we have started appreciating the power of quantum, it's amazing to see that the entire universe was created out of quantum fluctuation, and we know how to calculate them in certain scenarios of early universe, and that it's a rapidly expanding universe where these quantum fluctuations get stretched out so much that they behave like classical fluctuations and then can cause this density perturbations. And so that is consistent with the temperature anisotropy we see, and all the information in that plasma screen that we see. So if we believe they were formed due to these quantum fluctuations in the early universe, that mechanism will also create gravitational waves from the beginning of the universe. So that will really nail that we have understood the origin of the universe. And that is the next goal of cosmology. That's the must do to do. We haven't seen that signature yet. And to do that, we need to have a successor to this Planck satellite, which will have detectors which are much more sensitive. And in that context, we had proposed to ISRO a mission called ECO, Exploring Cosmic History and Origin, but it is more commonly known as the CMB Bharat, which is the Indian Cosmology Consortium, which proposed it. And it's supposed to be the ultimate uh, space mission, which will map out all the information that is relevant to cosmology present in the cosmic microwave background. So it has an amazing science promise, There's an ultra high goal, which is a for Nobel Prize category of measuring gravitational waves of quantum origin. You should remember that LIGO detection is of classical gravitational waves, classically generated gravitational waves. And then this is a high goal, but this is also there's a high risk of where you'll see it or where you'll see it. But then there are almost guaranteed high goals that we'll understand neutrino physics, we'll map out dark matter and all the ordinary matter in the universe, and vastly improve our understanding of cosmology if we were to launch such a satellite. And of course, whenever you are probing deeper into the universe, you always have unexpected discoveries, and that is always possible. So I'll stop here and say that Planck is the latest, provides the latest picture of the universe in the cosmic microwave background. It was launched in 2009. About 9 years later, we proposed CMB Bharat, and we hope someday ISRO will take it on itself and work with other space agencies to take on this quest, prized quest in fundamental science. Thank you, and I'll end with this slide. The universe, as I again, is vast. It's a lot to discover in the universe. Cosmology is just beginning, and I invite you all to take interest in understanding the universe. Thank you.
Yeah, thank you, Professor Tarun, for that wonderful talk. Interesting and captivating. Time to take questions from the
Yeah, I'm
participants.
happy to take some questions.
Right. So, yeah, you can unmute yourself and ask the questions, or you can raise the hand.
Yeah, so there is Dheeraj Bhardwaj who is the chat.
Yes.
Has asked a question in the chat. Um, chat.
So, shall I read it?
Yeah, you can read it out. Yeah, okay, chat is.
Sure. So, he is
So it
saying,
says, yeah, fundamental question. If the universe is expanding, its energy continuously increases. Um, yeah, that, but in that is one particular model where if you want to keep the universe this looking to look the same, if you assume a steady state universe, there you need to create matter continuously in an expanding universe to keep the universe looking the same. Here, the energy density actually is falling as the universe is expanding. Okay. Also, another interesting thing is we might ask where is this energy from expansion coming from that is diluting this? This comes from this conundrum that in general relativity, there are no global conservation laws. Okay. And this is something that one has to appreciate when you look at the universe. So, this is one of the surprises of general relativity.
right. So, are there other questions? While they are thinking, maybe I can ask one question. So, we know a very little about dark energy,
Mhm.
and you mentioned that this plays the repulsive effect under the
Yeah.
action of gravity. I mean, are there any experimental signatures for that, or just a
Yeah,
hypothesis?
the experimental signatures in the sense that this is, if you look at it like a fluid, then that fluid has negative pressure. And we also know that, understand the characteristic of the dark energy such that we believe that the negative pressure, the pressure energy density is the same as the matter energy density of the fluid. So the fluid has negative pressure, which is equal to the energy density. Okay, such things are not usually found, but in high energy physics, a false vacuum state will create such thing. Or you may have heard about vacuum fluctuations, that there are
Right.
vacuum fluctuation, quantum fluctuation. They have an energy density which is consistent with this. My personal take on this is Einstein theory allows for another fundamental constant called the cosmological constant. And that would also do the job. And to my mind, that is the most economical explanation at this time. That Einstein's gravity, we only looked at the Newton's constant part of it. But there's another fundamental constant called the cosmological constant, which is allowed by the symmetries and of general relativity and the theory of gravitation. So there's nothing inconsistent. And that cosmological constant can explain the same effect.
Right. Right. So it's the analogy could be that if we have a fluid which is flowing, and the objects in the fluid also will recede away from each other.
Yeah, so no, the way to think about this is typically, I if suppose I have a piston cylinder system, I have to compress the piston to make the gas hotter.
Right.
Here, if I compress the system, and so that means I'm adding energy by
Right.
doing work on it. Okay, but if the gas was funny and had negative pressure, then actually the gas, when it expands out, we think that the gas is doing work to expand the piston, right? So so gas is losing energy to expand. Here, the gas is actually gaining energy by pushing the piston out. So
Right.
that's why it accelerates the expansion of the universe.
Right.
Okay, negative energy density does. So we can create things which look like negative energy density in the lab, but not a uniform one. But anything which is any uh, phase which is in a caught in the false vacuum
Right.
has in principle a cosmological constant kind of behavior.
Right. Right. That makes sense. Dheeraj has one more question. It was a long one. How do we know
Okay.
there are galaxies of 100 s of million light year distance?
How do we know there are galaxies? We see the light from them. We can measure the spectrum of light, and we can see that the spectrum is redshifted. And then, if you believe we are in an expanding universe, then that amount by which it is redshifted, so basically blue light becomes red, and the change in the wavelength, ratio of the wavelength, gives you how much the distance is.
Right. He's asking if the light from different galaxies is reaching us at the same time. How do we distinguish between the
No,
galaxies?
but we look at different directions, right? So
Yeah.
a galaxy is in a particular location of the sky. So you focus the telescope to look at a very tiny patch of the sky, see one galaxy, measure its spectrum.
Right. So the sky location is important.
Yeah, by sky location, right? So yes, light is at that time also coming from another galaxy, but I'm not looking at that.
Right. And then Meet has a couple of questions. What are your views on trans-Planckian issues of early universe? People introduce theories like tachyocaustic cosmology,
Mhm. Okay,
string gas
so
cosmology.
Transplanckian issues of the universe are there, and in particular, they are challenges to these models of inflation. Uh, there are many other alternative ways of thinking about the universe, but essentially, every one of them has to create these perturbations. And depending on which one you're looking at, there are different levels of gravitational wave signature. The most thing that you believe in is an inflationary model. This is still something that people hold on to before they look at other options, because the other options, in my mind, are more contrived to make them work. But then it's a matter of taste. I mean, there are people working on the other approaches also. And the second question you have is, what do you think about constraining large-scale anisotropy in the universe using non-Gaussian? Would there be a way to realize Bianchi spaces? We ourselves have a paper way back in 2006 or something. Tuvin Ghosh, who is now a professor at NICER, was a undergraduate student project and then became my PhD student. We wrote a paper constraining Bianchi models, the anisotropy that can come from it. Later, of course, there are many other ways you can, I mean, many more refined uh, limits that have been put. So you can, yes, you can put large scale anisotropy constraints on large scale anisotropy in the universe. It's non-Gaussianity of a particular kind. It's not really non-Gaussianity, but it creates a violation of what is called the isotropy, statistical isotropy. But you can also see non-Gaussian signatures in some cases associated.
Right. Are there any other questions? If not, then maybe
Uh,
probably I will. Yes.
uh, this is Jagriti sir. I am a bit curious about the fact that you discussed that the distribution of the galaxies in universe is isotropic and homogeneous in nature. So
Hmm.
this is correct to what extent? Because there can be some significant differences from one point to another point in the galaxy.
Yeah, so
So
it
isn't
is.
it can introduce some error in our theoretical calculations?
Yes, so there are. I mean, so when I say this assumption of isotropy and homogeneity holds at the scales of hundreds of megaparsec. Okay, so that is 300 million light years size. Okay, so on those scales, it is homogeneous, right? Suppose if you look at the desert, you'll say, okay, there's a homogeneous distribution of sand, but on the scales of the grains of the sand, obviously, every region will be different, right? So then you invoke something called statistical homogeneity, which is saying how much on what volumes you have to average, and that average doesn't change then. And so for the universe, you have to average on hundreds of light year scale boxes of hundreds of light year scale. So you're right. If I just go to a point, the universe will look very different at different places. But if I were to measure the universe on the average over such big volumes, and we can do that because we have surveys of the galaxy. So you can take the average number of galaxies in volume, say 100 megaparsec, then you will see that more or less the same number of galaxies everywhere
So is
statistically.
it an approximation type of thing?
It's approximation, yes. So every time if you do any physics, you should realize all physical laws are approximations to nature. Right? Newton's laws were an approximation. They have been improved by special relativity on one end when the velocities are large, and laws of Newton's laws of gravitation have been replaced by Einstein's gravity. But it nevertheless, Newton's laws work very well in an approximate way. And Einstein's gravitation may be also an approximation to some theory that we don't know. This is the whole story of science, right? We keep improving as we dig deeper, and that's the whole thing of what I call frontier science, right? You are looking at the frontiers of our fundamental understanding of various things.
I have one more question, sir. That are the galaxies really moving away from us, or is it just the space which is expanding?
Space, which is
And
expanding. So it's very important question. So the galaxies are actually stuck at the same spatial point in the space time. It's just that the distance between them is increasing because the space is expanding in between. Okay, which also brings me to a thing which I tell a lot of people that, I don't know how many of you are Star Trek fans, but nowadays warp speed is not something which is people even worry about. So, people basically move at speeds much higher than the speed of light. In principle, general relativity allows that. I mean, it's difficult to conceive how you would do that, but I can move to a very distant galaxy very fast if I have a machine that contracts space in front of me and expands it behind me. Okay. So such things are allowed by general relativity. And it's important to realize because you never know how many centuries down the line we may be able to manipulate things at that level. But it is that space-time is flexible. So galaxies are not actually moving much. It's a space between them that is growing.
and sir, will the universe will expand forever, or it will recollapse at some
Yeah,
point?
I mean, at this point, that's the thing. So earlier we didn't know. Now we are sure that if this cosmological model is correct, and we see no deviations till now, then the universe will keep expanding at a larger expansion rate. It's accelerating in its expansion. It will get expand forever, and it will expand at a faster and faster rate. As consequence of that, will soon the distant galaxies that we are seeing now will drop out of our light cone. Okay, so in these such universes, you create something called a event horizon in the future, where you cannot see beyond a particular distance in the universe. So, and very far in the future, essentially we will have only the gravitationally bound area around us that we can see. The rest would have been expanded away, and we can't see them anymore. It's a lonely universe, very lonely future for the universe.
So is it like the universe is infinitely large?
Yes, that is again the simplest idea you can have. There are thoughts of universes which are geometrically flat, but nevertheless they are finite in size. These are called toroidal universes. They are something called cosmic topology. But we know that this kind of topological identification is certainly much bigger than the observable universe that we have. So it's then becomes a point of metaphysics as to whether the universe is. It need not be infinite, even if it is geometrically flat. That's an important point to keep in mind. Nothing in our fundamental physics or maths prevents that.
Thank you. Maybe probably we can take one last question, short one,
Okay.
in the interest of time. So in the last slide, yes,
It's
Sujat.
कि we are saying कि the universe is infinitely large, but as we know that the Big Bang thing has happened, so the universe is not originated from a single point, that singularity or thing.
Yeah, so singularity is a question that we cannot address in physics. So, the picture that I showed you at the end, if you can still see it, the idea we have in cosmology is the universe is some messy space-time manifold. Only a small patch of it expanded rapidly and gave you a very uniform
You are
patch.
not audible.
Oh, I'm not audible.
No, no, you are
Any,
audible. Yeah, you are audible.
I'm audible, right?
Yeah, you are audible.
Okay. What about Jagriti? Can you hear me?
Maybe some network issue at her end.
Ah, she has
Yeah,
dropped. Okay.
she has left. Right.
Okay.
So at this interface between the universe, this
Yeah.
random structure, you have put them
Yeah. So this
yourself.
is our picture of the earliest universe. It could be something that we'll never figure out.
Mhm.
But only a small patch of that is creating the universe that we can see. And that is smooth, homogeneous, nice, and it fits the cosmological model,
Right.
right? But some other patch may be giving you a universe which is totally different. So there are people talking about multiverses and things like that. And multiverses stacking into each other, leaving signatures. But these are exotic possibilities that
Right.
you can always think of.
Right. You ended your presentation with a very interesting, ambitious mission of CMB Bharat, the
Yes.
quantum signature of gravity. Can you just briefly tell us what experiment are to be designed, what principles we are going to use to
No, so
detect this?
this could basically be a detector in hundreds of gigahertz. It will have detectors that ranging from tens of gigahertz to about almost 1,000 gigahertz, multiple bands,
Right.
and it will have detectors that are sensitive enough to measure 1 attowatt of power, 10 to the minus 18 watts of power.
Oh, wow.
Now, your cell phones can already measure picowatts of power,
Mhm.
and the detectors that are improving give you cell phones that 5G and all that are moving to frequencies where you have much more sensitive detectors. Now, these detectors operate now at cryogenic temperatures, hundreds of millikelvin. So you have to have a satellite which can separate out the hot part where the solar panels are, the hot electronics are, and then a part where the microwave. And this has been done for Pla. Only thing is the detectors that we require for CMB Bharat are already there. They are being deployed on the ground, but from the ground we have some limitations because the atmosphere is there
Right.
and it varies even in the best of sites. So a space provides a very stable platform from where to see it.
Right.
And our whole idea is to fly these detectors in space.
Wonderful. Wonderful. Yeah, if there are no more questions, let us thank Professor Souradeep for this wonderful talk. I mean, I personally want to thank him for taking time and interacting with the student.
Yeah, it's my pleasure. Thank you
Yeah,
so much.
thank you so much, sir. See you again.
Okay, wonderful.
Yeah, bye bye.
Bye.